Hello, Hopewell. This is Mr. Steinberg. Today's lesson's 8.5, all about hyperbolas. It's our last conic section that we're going to study, and let's explain what that means. So we know that conic sections are the cross sections of cones, and here's today's one. I'm actually going to use two cones that are connected at a vertex to make a hyperbola. Let's say we have two connected cones and they both share this vertex, and I slice it with a plane just straight down. So if I cut it right there, the intersection of that plane and the two connected cones would make two branches of a hyperbola. Now we've studied hyperbola before. We've studied hyperbolas in chapter 5, but these are a lot different. These conic section ones are have way different equations, and you can see the equations that we're going to discuss today. And we're going to also talk about the similarities between graphing ellipses and graphing hyperbolas because of the nature of these two formulas. By the end of class, I want you to be able to draw some hyperbola, also analyze an equation, and describe the characteristics of the hyperbolas. So let's get started. The definition of what a hyperbola is, it's a set of points that have the same difference of their distances to two set points or two fixed points. What that means is, imagine if you measured the distance from point P to focus 1 and point P, the same point, to the other focus 2. If we take the long length and subtract the short length, that gives you a number. That number is the same number no matter where you are on the hyperbola. You could be all the way down here, and this would be let's call it point Q. Measure the distance between point Q and this first focus, and point Q and the second focus. Take the long length and subtract the short length, it would be the same number. And that's really the definition of a hyperbola. Sometimes the pictures of our hyperbolas, they differ. They may look like this one or that one. And that all matters and depends on what the equations look like. The first thing that's striking me is these equations have both x squared and y squared, just like the ellipse does and just like a circle does. The biggest difference in why it's not looking like a circle or an ellipse is that there's a minus sign in between the x squared and the y squared. Also, what I notice is both of these equations end in 1, just like the ellipse formula. So if I'm looking to distinguish a hyperbola from an ellipse, I'm looking for a minus sign between an x squared and a y squared. I'm also looking for the equation to equal 1, and if it doesn't, I might be able to manipulate it in such a way that it can. The next thing that I'm taking a look at is what makes and causes a hyperbola to open horizontally versus vertically. The equation for the first hyperbola has an x squared in front of a y squared that's negative. When the x squared is the positive variable and the y squared is negative, your hyperbola is going to open horizontally. There's really a term that I'm going to use right now for the very first time, and it's called the transverse axis. The transverse axis is a line that connects either of the two foci, and by the way, those foci are the two set fixed points. It's a line that connects the two foci, but it also connects these points called the two vertices, and it also runs through the center. So this transverse axis is horizontal, and that's because the x is the square value that's positive. It's a squared variable that's positive. When the y variable is the square variable that's positive, then your transverse axis containing the two foci, the two vertices, and the center runs vertically. That's the distinguishing feature in how you can determine if your hyperbola opens outwards, left and right, horizontally, upwards and downwards, vertically. It's which variable is the positive squared variable. What does it begin with? So these are some of the similarities and differences. Also, just like a parabola, the focus is on the inside of each branch. So it's really outside of this rectangle. And we'll talk about how you make this rectangle and what it's there to do. I also noticed that there's two diagonal dotted lines within this picture. Those will be very helpful. Let's take a look at the two equations as we discussed them a little bit. Actually, I don't want to move it too down. I kind of want to see everything right here. So we have these kind of two equations, and they are different. When the x is the squared variable that's positive, we have a horizontal transverse axis connecting the two foci and the vertices and the center. And we have x squared over a squared, that's similar to an ellipse, a y squared over b squared, that's similar to an ellipse, and it equals 1. The only difference is the minus sign. Now when they switch the x and the y, the a squared and the b squared don't go with it. The a squared, it says note, the a squared is always underneath the non-negative variable term. So the a squared is always going to be first and the b squared is always going to be last. This is where it gets confusing. The dotted lines that I spoke about in these pictures, these are the asymptotes of your hyperbola. If you remember back in chapter 5, we graphed a hyperbola, and as you went farther left and farther right, the graph would get closer and closer and approach this asymptote. And same with these hyperbolas. The farther I go left, the more down or up this graph will get closer and closer to these asymptotes. This is where it gets confusing. Sometimes the asymptotes are diagonals with slopes of positive b over a, or negative b over a, or positive or negative a over b. So I like to make things easy for you. What I remember is that the slope, I don't really want to remember which one's a and which one's b. I don't really need to, especially because when we take a look at this focus equation, if we're adding a squared and b squared, there's no real differentiation between which one is what. I can change them, and I'll get the same value for c squared. So here's what I want to do to remember which variable goes on top and bottom when you're finding the slopes of these asymptotes. Slope is always the change in y divided by the change in x. So if I want to do the change in y, I'll take the numerator from underneath the y. I'll take the denominator from underneath the x. So I'd square root b squared to get b, put that in the top. I'd square root a squared to get a, and put in the bottom. That's the change in y divided by the change in x. And watch, this also works for the second one. The change in y is a, the change in x is b. So our slope is a over b. That makes things a lot easier. To find the location of the foci, we use this, which looks like the Pythagorean theorem, c squared equals a squared plus b squared. But we're not talking about right triangles right now, but it is the same formula. Why does this formula make sense? Think back to an ellipse. When we had a plus separating these two terms, the x squared and the y squared, this was a minus sign in your focus equation. We wanted the focus for an ellipse to be internal inside of the ellipse. But for a hyperbola, the foci are located external, away from the center, farther away from the center. So we're going to add the a squared and the b squared. This makes a little bit of sense to me. There's one mathematical exercise at the bottom, which they worked out for us, but we'll just take a look at what they did. It says, identify the characteristics for the hyperbola with the following equation. Let's see if I forgot to mention anything. I don't know if I mentioned like vertex. Maybe we'll go back. Let's go back. How do you find the vertices? Well, to determine if the vertices are above or below center, or to the left or to the right of center, again, we want to look at which variable is the positive squared variable. Is it the x or is it the y? When it's the x, the vertex is left or to the right, but how many units? A units. Where do we get the a from? Here, underneath the positive term. Underneath the positive variable squared term, you get the a squared. So we're going to square root a squared and move right and left a units from the center. The a is again underneath the positive squared variable. In this case, we're not going to go a right and a left because the a is underneath the y. We're going to go a units up and a units down. A units up is one vertex and a units down. So what I didn't mention about vertices, I now mentioned. Also, you'll notice there's no such thing as a covertex or covertices for hyperbolas. So let's get back to this one. Example 1. Identify the characteristics for a hyperbola. So what are the characteristics? We want to know the center. We want to know the location of the vertices. And we want to know the location of the foci. And we want to know the equations for the two asymptotes. So let's find the center. I can't tell the center here because it's not in the appropriate form. I need this to equal 1. So it says divide everything by 100. That gets us to our second equation. Now that it's in the regular form that I'm used to, I can understand that the center is 0, 0. So the center in this exercise is 0, 0. Because the y is the positive squared variable, our transverse axis, the axis that connects the vertices and the foci and the center, is the vertical. So our hyperbola will open up and down. Which means what? In order to find the vertices, I'm going to go the square root of 4 units up and down away from the center of 0, 0. Let's go 2 units up. Let's go 2 units down. These are our two vertices, 0, negative 2 and 0, 2. Where are the foci? We're going to add a squared plus b squared. 4 plus 25 makes 29. So c squared equals 29. The value of c equals plus or minus square root of 29. If our transverse axis is vertical, the foci are going to be root 29 above and root 29 below the center. So because our center is 0, 0, we're going to add these to the y-coordinate. That's how we got foci at 0, comma, root 29 and 0, negative root 29. 0, comma, negative root 29. Finally, I don't know if you noticed this, but there is a typo here. Somebody forgot to type an x here. The two equations for the asymptotes of this graph, if we were to graph them, are y equals positive or negative 2/5 x. How do we get this slope, or these two slopes? Remember, slope is always the change in y divided by the change in x. The change in y is the square root of 4. The change in x is the square root of 25. The square root of 4 is 2, the square root of 25 is 5, and y goes above x. It's not first and last, it's change in y over change in x, so 2/5. One asymptote will go up to right 5, the other asymptote would go down to and right 5. Also, the asymptotes must pass through the center. So if you're making equations for your asymptotes, make sure you pass them through your center. Please continue to the next video.